Welcome to the deep dive. Today, we're getting into something absolutely fundamental to modern computing. I mean, just think about it. The demand for raw compute power, especially with AI, machine learning, high-performance computing, it's just exploding, right? Data isn't just the new oil. It feels more like the lifeblood. And getting it where it needs to go fast is everything.
It really is paramount. And, we saw huge leaps with PCI Express 5.0, pushing data rates to 32 gigatransfers per second, GTs. That was a big deal. But the sheer sort of exponential growth in processing power, particularly with those advanced GPUs and AI accelerators, well, it quickly became clear that even PCI 5.0 was turning into a bottleneck. This created what people started calling the exascale imperative. Basically, we needed an even faster data fabric, like yesterday.
And that's where our star player comes in, PCIe 6.0. This isn't just, a little speed bump. We're talking a staggering 64 GTs per lane. That effectively doubles the bandwidth of Gen 5 to a mind-blowing 256 gigabytes per second in a standard by 16 setup. But the real story here, the game changer, isn't just the raw speed. It's a fundamental architectural shift, a paradigm shift, really. So our mission today is to unpack the three interdependent tech pillars that made this happen and how they completely redefined the whole process of link setup, link training, solving problems right at the edge of what's physically possible. Think of this as your shortcut to understanding the complex magic under the hood of your next-gen systems.
Okay, so let's unpack this. When we talk PCIe 6.0, yeah, the first thought is faster, but you're saying engineers had to totally reimagine the architecture. What was the big wall they hit? That's exactly right. The sheer demand for speed just ran smack into the physical limits of copper interconnects. The traditional ways just wouldn't work anymore. Trying to just double the speed like before, it would have led to an impossible situation physically. So to get around that, they came up with these three crucial technologies, and they became this inseparable triad, each one absolutely depending on the others.
Right, makes sense. So the first big one, PM4 signaling, if they had stuck with the old way, NRZ signaling, doubling the speed meant doubling the frequency to 32 gigahertz. What was the killer problem with that?
Well, at 32 gigahertz, the signal loss in standard materials, the PCBs, the connectors we use every day, it would shoot up to over 60 decibels, 60 gigahertz. That's a massive amount of loss. It makes it physically impossible to recover anything usable to the receiver. The signal just gets completely lost in the noise.
Wow. Okay, so a dead end. And the solution was PM4. So instead of just 1 bit per symbol, like on-off, PM4 uses 4 voltage levels to encode 2 bits. That's a clever bit, right? It doubles the data throughput without pushing the frequency past 16 gigahertz, same as PCIe 5.0. It's like sending twice the mail through the same size slot.
No.
But there's always a but, isn't there? What's the trade-off?
Well, there's a big one, absolutely. Well, it's super clever. It comes at a significant cost. A severe 9.5 dB hit to the signal-to-noise ratio, the SNR. Think of the signal I that clear opening receivers need to read the data. With PM4, it's only 1/3 the height of an NRZ signal's I. That makes it incredibly vulnerable to noise, interference, everything. You're trying to tell the difference between 4 voltage levels that are much closer together instead of just 2 far apart ones.
Okay, so that much lower noise margin, that leads us straight to the next pillar, right? Forward error correction, or FEC. Because PAM4 is so susceptible to noise, the basic error rate, the bit error rate, or BER, is way higher, something like 1 error in a million bits, which is worlds away from the old PCIe requirement of less than 1 in a trillion. So just hoping for a clean channel wasn't going to cut it anymore, was it?
Not even close. Exactly.
Yeah.
So PCIe 6.0 mandates a lightweight, low-latency forward error correction mechanism. And this is really revolutionary for PCIe. Gen 6 basically shifts from trying to avoid errors to actively managing errors. It accepts errors are going to happen frequently, but it's designed to correct most of them on the fly.
So it's less about building a perfectly smooth road with 0 potholes and more like equipping the car with an amazing suspension and instant pothole repair kit. That's a huge philosophical shift, isn't it? That's a great analogy, yeah. The designing for imperfection right from the start. It's about building a resilient system that can cope and self-correct instead of this constant, near-impossible battle against physics to get a pristine signal at these speeds.
Okay, and that brings us neatly to the third piece of the puzzle, FLIT mode. If FEC is now actively fixing errors, does that change how the data itself needs to be packaged or structured? It absolutely does, yeah. For an FEC system to be efficient and low latency, it really needs to work on fixed-sized chunks of data. And that requirement basically forced the introduction of Flow Control Unit mode, or FLIT mode. Now, all data, no matter what it is, TLPs, DLLPs, it all gets transported in these fixed-sized 256-byte UCLOTs at the physical layer and the data link layer. And this change just ripples through the whole stack, affects packet formats, credit management, how retries work, everything. So if you step back and look at the big picture, you see these three aren't just separate features. They're completely intertwined. PAM4 made FEC necessary, and FEC made FLIT mode necessary. You just can't have Gen 6 without all three working together. It's truly an inseparable triad.
Right. PAM4, FEC, FLIT mode. Three massive architectural changes. So what does this all mean for how two PCIe devices actually, connect and start talking? I'm guessing the LTSSM, the link training, and status state machine is still the brain behind that operation.
Oh, absolutely.
Yeah.
The LTSSM is still the logical heart. It's responsible for negotiating, well, everything. Link width, speed, equalization settings, all that stuff. It manages this by exchanging special packets, these things called ordered sets.
And FLIT mode throws a wrench in the works here too, I hear. It gets negotiated really early on, right? During polling and configuration states, using a specific FLIT mode supported bit in these things called TS1 ordered sets. But then there's this sticky aspect.
That's right. And this is where it gets really interesting from a state machine perspective. Once a link successfully negotiates and enters FLIT mode, which happens when it trains up to 64 GTs, it is stuck in FLIT mode for its entire operational life, even if it has to drop speed later. This creates these totally new hybrid states. So imagine a 64 gig link hits a signal problem, maybe some noise, it needs to drop back to 32 GTs. It retrains to 32 GTs, but it stays in FLIT mode. So now you're running Gen 5 speed, 32 GTs, NRZ signaling, but all your data is still packaged in those 256-byte FLITs. It's a very unique combination.
Wow, that's pretty wild. So FLIT mode is like a one-way street once you hit 64 gigatransfers. And the stickiness, does it enable anything else? I think I read about a new power-saving feature.
It does, yeah. A natural question then is, how can we save power dynamically without causing huge latency stalls? The answer is L0P. That's L0 partial. It's a new active state power management feature, kind of a substate of the main L0 active state. And crucially, it's only available when the link is operating in FLIT mode. What L0 lets you do is dynamically scale the link width down, say from by 16 down to by 8 or by 4, even by 1. It does this by putting the unused lanes into electrical idle. And this is the key, it does it without interrupting data flow on the lanes that are still active, which is a massive leap. Before, changing link width meant a full retrain, stopping all traffic for microseconds. L0P transitions are seamless, totally transparent to software. Pretty neat.
Very clever. Okay, but going back to the initial link setup, given how noisy and difficult PAM4 is, how on earth do they even get the link started? Bootstrap it, as you said, when the signal is so fragile initially.
Yeah, the challenge is just so extreme with 64 GTs that they literally had to invent a completely new training sequence just for bootstrapping that speed. It's called TS0, Training Sequence 0. And the fact that it even exists tells you how tough the signal integrity problem is. The genius of TS0 is that it's designed to be electrically equivalent to an old-style NRZ signal. It only uses 2 of the 4 PAM4 voltage levels, level 0 and level 3, the outer ones. This makes a much simpler signal, electrically speaking. It allows the receiver's complex equalization circuits and its clock data recovery, or CDR, to get a preliminary lock, kind of find the basic signal timing. And it does this without having to deal with a full, noisy, three-eyed PAM4 signal right away. It's like a foundational step. Establish a basic stable connection first, before you try to train the full-speed PAM4 link using the normal but redefined TS1s. It's a really brilliant engineering workaround.
That is a seriously clever trick to get things off the ground. Okay, so we've covered the logical heart, the LTSSM, these new signals, modes like FLIT and L0P. Let's dive into the physical reality now. Getting a 64 GT's PAM4 signal to actually work. You said it's not just about making it better, it's about making it exist at all.
Exactly. You've got it. Without equalization, the eye of a 64 GT signal is completely closed, shut tight. So this equalization process is not just tweaking or improving the signal, it's actively creating a decodable signal from what starts as basically unintelligible noise. It's an absolute prerequisite for the link to even function. Remember that 9.5 dB SNR hit from PM4? That makes the link just acutely vulnerable to everything. Noise, jitter, reflections, crosstalk is a huge one. And on top of that, they actually tightened the total insertion loss budget, how much signal you're allowed to lose, end to end, down to 32 dBs from 36 dBs in Gen 5. So without really robust equalization and that error correction we talked about, a 64 GT's link just wouldn't be usable, period.
Right. So with all that unavoidable noise in the closed eye, how do they guarantee the data is actually accurate? Is it just the FEC doing all the heavy lifting?
It's a tag team effort, actually. This is where you really see the fundamental shift to error management in action. It's a symbiotic two-stage system, FEC, and the good old cyclic redundancy check, or CRC. The lightweight FEC is the first line of defense. It's designed for super low latency, less than 2 nanoseconds added. It uses this thing called an interleaved Reed-Solomon code. And crucially, every single 256-byte FIT carries 6 bytes of this EC CETA. The interleaving part is key. It gives resilience against burst errors, like a burst of up to 16 bad symbols on one lane. It'll likely corrupt at most 1 symbol per ECC group, which the code can then correct. So FEC handles the high volume of relatively simple errors. Then, after FEC has done its thing, the receiver checks a strong 8-byte CRC that's also part of the FLIT. If that CRC check fails, it means the error was too complex or too widespread for the FEC to fix. That failure triggers a negative acknowledgement in a TAE back to the transmitter, which then triggers a link-level retry of that FLIT. This combination is incredibly efficient.
You've got fast FEC handling the common, simple errors, and the robust CRC catching the rarer, more complex ones, leading to a retry only when absolutely necessary. The target link retry probability is super low, around 5 times 10 to the minus 6. It's an elegant way to live with an imperfect channel.
Okay, that makes sense. A two-pronged approach. And the actual equalization process itself, the dance, as you called it, you mentioned phases.
Right, the multi-phase equalization dance at 64 GTs. First, there's a strict rule. A link must first train successfully and be stable in the L0 state at 32 GTs Gen 5 speed before it's even allowed to attempt 64 GTs. You can't just jump straight from, say, Gen 3 speed to Gen 6. No skipping steps. This ensures you start from a known good, stable foundation. Then, the process uses those special training sequences. It has 4 phases. Phase 0 and Phase 1 involve exchanging those TSCs, the simpler, NRZ-like signals we talked about. This is for getting that initial lock, evaluating the channel characteristics, aiming for a preliminary BER, better than 10 to 4, sort of roughing things in. Then, in Phase 2 and Phase 3, they switch to using full PAM4 TS1s. Now the devices start iteratively fine-tuning their transmitter settings, the receiver giving feedback, until the signal eye is fully open and they achieve that final target BER of better than 10-12.
And achieving that level of precision, really opening the eye of that noisy PM4 signal, I bet that required some beefed-up hardware on the transmitter side for equalization.
Absolutely needed, yeah.
Yeah.
A big upgrade in Gen 6 is moving from a 3-tap finite impulse response, or FIR, filter in the transmitter, to a more powerful 4-tap FIR filter. This adds a second precursor tap called C2. Basically, it gives the transmitter more granular control over the shape of the signal it sends out. Lets it precompensate more effectively for the distortions it knows the signal will encounter down the channel. The spec defines 11 new standard Q presets for this filter at 64 GTs, Q0 through Q10. These are sort of starting points, pre-configured settings. The receiver then uses feedback, embedded in the TSCs and TS1s, to tell the transmitter which preset looks best or request fine-tuning adjustments. Increment this tab, decrement that one. And it's fascinating, actually. Modern validation teams are even leveraging machine learning techniques to speed up this incredibly complex tuning process in post-silicon testing. Gives you a sense of how cutting-edge this stuff is.
Wow, ML optimizing PCIe links. That's something else. It just sounds unbelievably complex, both designing it and then making sure it works reliably under all conditions. How do engineers even start to verify this level of intricate tuning?
Yeah, that's a huge challenge. It comes down to incredibly rigorous, extensive simulation before silicon is even made, and then equally intense testing afterwards, often involving custom-built test gear, high-speed scopes, and yes, even AI now. To model and predict signal behavior under countless scenarios, it's a massive effort.
Okay, let's shift gears slightly. A huge part of PCIe's success over the years has been its amazing backward compatibility. You could usually plug an old card into a new slot or vice versa, and it just worked. But with all these fundamental changes in Gen 6 PAM4, FLIT mode, the whole shebang, how does that tradition hold up? Sounds like it could be tricky.
It's still a cornerstone, absolutely. But you're right, with Gen 6, just saying backward compatible is, well, it's an oversimplification. Its behavior is totally conditional on what the link manages to negotiate. Let's take the simple case first, what you might call true backward compatibility. Say you plug a brand new Gen 6 graphics card into an older motherboard with only a Gen 5 or maybe even a Gen 4 slot. The Gen 6 card will advertise, hey, I can do FLIT mode. But the old port, the root port on the motherboard, it doesn't understand FLIT mode. It doesn't support it. So the negotiation fails for FLIT mode and the link never enters it. It trains up entirely within the legacy framework. Uses NRZ signaling, the older 128B, 130B encoding. Everything operates at the highest speed. Both sides mutually support in that legacy way. Maybe 32 GTs, maybe 16 GTs. Now, what this means under the hood is that the Gen 6 device's SerDes, that's the chip doing the serializing, Deserializing has to be incredibly complex. It's got to be this multimodal engine capable of running in the new PAM4 flaky world and all the older NRZ modes, too. It's quite a feat of engineering.
Got it. So it's smart enough to detect the older partner and just reverts completely to the old ways. But what about the other scenario, the hybrid mode you mentioned earlier? Two Gen 6 devices, they successfully train up to 64 GTs, FLIT mode is active. Then, oops, some temporary signal issue happens. What happens then? Does it fall back to a pure legacy mode?
Ah, no. This is where that sticky fussy rule really bites. Remember, once you enter FLIT mode by hitting 64 GTs, you're stuck there. So in your scenario, two Gen 6 devices, link established at 64 GTs, then a transient issue like maybe a temperature fluctuation or some vibration, the link stability falters. It'll likely drop into the recovery state in the LTSSM and try to retrain at a lower, more stable speed. Let's say it successfully retrains at 32 GTs. BT, because it had already been in FLIT mode at 64 GTs, it is obligated by the spec to remain in FLIT mode even at 32 GTs. So you end up in that unique hybrid state, FLIT over NRZ, running at Gen 5 speed, 32 GTs NRZ, but still packaging all data in 256-byte FLIT-Ts. And this is not traditional backward compatibility. It's a specific fallback mechanism defined within the Gen 6 standard itself. Verifying this hybrid mode works flawlessly is a absolutely critical and tricky part of validation for Gen 6 devices.
Okay, wow, that adds layers of complexity. So if devices can be running in pure legacy NRZ mode or this hybrid FLIT over NRZ mode or full Gen 6 FLIT mode, how do you possibly connect all these different generations and modes together in a complex system like a big server? Seems like a recipe for chaos.
Right. This immediately raises the question, who manages this potentially chaotic ecosystem? And the answer is the modern PCIe switch. These switches aren't just simple data repeaters anymore. They've evolved into highly intelligent fabric managers. A absolutely fundamental capability they have is negotiating the link speed, the width, and importantly, the mode, FLIT or non-FLIT, independently on every single one of their ports. That's how a single switch chip can simultaneously talk Gen 6 speeds in FLIT mode to a new GPU on one port, Gen 5 speeds, non-FLIT, to an SSD on another port, and maybe even Gen 4 speeds to a network card on a third port, all at the same time. But this ability leads directly to what is arguably the most significant interoperability challenge introduced by PCIe 6.0, and that's the FLIT non-FLIT translation challenge. Imagine data needs to flow from the Gen 6 GPU running at 64 GTs, fully in FLIT mode across the switch to, say, a Gen 5 NVMe SSD that's running at 32 GTs in traditional non-FLIT mode. The switch can't just mindlessly forward the data packets. The formats are totally different. It has to perform complex, on-the-fly translation between the two modes, in both directions.
It's acting like an intelligent Layer 3 gateway. Deeply aware of the PCIe protocol, it has to parse incoming data, understand its meaning, and then reconstruct it in the correct format for the outgoing port.
Whoa. Okay, that sounds like a huge task for the switch. Can you give some examples of what it actually has to translate on the fly between FLIT mode and non-FLIT mode?
Oh yeah, it's significant. For starters, the packet headers are completely different. FLIT mode uses a different transaction layer packet, or TLP, header format than non-FLIT mode. So the switch has to literally parse the incoming header from one side, figure out what the TLP is trying to do, and then construct a brand new, correctly formatted header for the other side, every single packet. Then there's the whole retry mechanism. Non-FLIT mode uses acknowledgments, AKK, at the TLP level for error recovery. FLIT mode does its acknowledgments and retries at the FLIT-P level, tied into that FECCRC system. The switch has to act as a proxy between these two different worlds. It terminates the retry protocol on the incoming port and independently manages the protocol on the outgoing port. It has to keep track of what's been acknowledged where. Another example. FLIT mode expands the tag field used to track outstanding requests, up to 14 bits. Non-FLIT mode uses fewer bits, maybe up to 10. The switch has to somehow map these tags between the domains. What happens if a 14-bit tag comes in from the FLIT side, but the non-FLIT side only supports 8 bits? The switch has to manage that, potentially stalling the transaction or reporting an error. It's a really non-trivial amount of logic, requires significant buffer memory within the switch. And a bug in this translation logic, it can be catastrophic, silent data corruption, system deadlocks, even if the electrical links on both sides look perfectly healthy.
Man, that sounds incredibly complex and fraught with potential issues. How does the industry even build confidence that this all works between different vendors' equipment?
Yeah, with this level of complexity, no single company can possibly ensure interoperability on its own. It absolutely requires industry-wide collaboration. The PCI SIG, the group that defines the spec, plays a huge role. They host regular compliance workshops, and maybe more importantly, these things called plug fests. Plug fests are basically events where dozens of companies bring their pre-production silicon cards, motherboards, switches, test equipment, and physically connect them together in every combination imaginable to find and fix interoperability bugs before products hit the market. Beyond that, key ecosystem players, companies like Broadcom, Astera Labs, who make retimers and switches, storage companies like Micron, test equipment vendors like Teledyne, LaCroix, many of them have set up their own dedicated large-scale, cloud-scale interoperability labs. They do continuous, rigorous testing in real-world configurations. So when you see announcements about, say, a specific Gen 6 switch successfully interoperating with a particular Gen 6 SSD and being verified by a certain protocol analyzer, those are really significant milestones. They build confidence across the industry that this incredibly complex ecosystem is actually maturing and becoming ready for deployment.
Okay, so let's bring it all back home. Our mission was to unpack PCIe 6.0, and it's clear this is way more than just a speed bump. It really feels like the most significant architectural evolution in PCIe's entire history. We've seen that tightly coupled triad PAM4 signaling, forward error correction, and FLIT mode, and how they didn't just enable speed, but fundamentally redefined link training, equalization, error handling, the whole works. It's been a fascinating deep dive into pushing physical limits.
Absolutely. And the long-term consequences are profound, especially that interoperability piece we just discussed. It marks this new frontier where the PCIe switch isn't just a conduit, but has evolved into this intelligent protocol-aware gateway. Its translation capabilities are really the linchpin holding the whole mixed-generation ecosystem together. And if we connect this to the bigger picture, looking forward, you can really see that the architectural foundation laid down by PCIe 6.0 is not just for today's systems. The next generation, PCIe 7.0, which is already in development and aiming to double the speed again to a mind-boggling 128 GTs per lane, well, it's going to build directly on the PAM4 and FLIT mode framework that Gen 6 established. This really solidifies these core principles: active error management instead of avoidance, fixed-size packet transport with FLITs, and intelligent switch-based fabric management. It makes them the enduring paradigm for computing in the exascale era. So, yeah, understanding these seemingly tiny, deep technical details, it's actually pretty essential if you want to grasp how high-performance computing is going to keep evolving and scaling into the future.